So let's start with what density is. Well, density is a simple thing. It's like density in physics. But in physics, we deal with volumes and with masses. In this case, we don't have volumes and masses, but we have the beans, and then we have the numbers of values, okay? So the density, we can define density as how many values in percent in a unit bean. For example, let's talk about height of people or weight of people. Let's say we have a bean between 60 and 70, okay? So that's the bean. Then we have, for example, 4 values here. Let's say the total number of values in our sample is 10. So it means that in this case, the relative frequency will be 0.4. So it's 40% of the values, okay? So, but these 40% are in the whole bean, and the whole bean is 10 kilograms between 60 and 70. 10 kilograms, okay? So how to calculate the density? We can calculate density just by simply taking this value and dividing to the size of the bean. So the density is 0.4 divided to 10, which gives us 0.04 or 4%. So it means that if you split this into small subintervals, 1 kilogram each, the average density, the average number of values in each subinterval will be 4, and that gives you the density. So how dense the values are in this bean, or how comfortable, if you can think about that, how comfortable they feel in this bean. Okay, so. And if we make a distribution histogram using densities, we just use a density value for the height of bar. For example, in this case, if we use relative frequency for the relative frequency distribution, this will be the bar 60 and 70, and then this is the bar, and the height of the bar that corresponds to the relative frequency is 0.4. If we use density distribution, that will be the bar 60 and 70, and the height of the bar will be a density, so it will be 0.04. But area of the bar will correspond to the relative frequency, so you can calculate it easily. So you take the density 0.04, and then you multiply to the width of this bean to 10, so you will get 0.4. So when you use density distribution, area of bar is the relative frequency. In this particular bean, okay? You can prove it using a different way. So we know that density is the relative frequency divided to the width of the bean, okay? To the width of the bean. So it means that the relative frequency, its density times the width of the bean. I will just use W. But we know the density, it's the height of the bar, so it means that it's height multiplied to width, and that's the area, of your bar. Okay. So when you use density distribution, area of each bar corresponds to the relative frequency in this bean, in the bean that corresponds to this bar. Okay. Now let me show you another property of density distribution, comparing to relative frequencies. Let's say we have a sample. Let's talk about weight of people again. So we have a sample, size of the sample is 10. So we have 10 different persons, and we have measured the weight of these persons. And let's say we have some values like 81, 82, 84, and 87. Okay. It's just 4 values out of 10. And then we have a bean between 80 and 90. Let me just draw it like this. So we have 80. We have 90, and we would like to make the relative frequency distribution. So first we calculate the frequency. The frequency is 4 in this case because all 4 values are inside this bean. So it means that the relative frequency will be equal to 0.4 because we have 10 values in total. So it means that we can make a drawing like this, 0.1, 0.2, 0.3, 0.4, and that will be the bar. Okay, so this is 0.4. So that's the relative frequency distribution, where height of bar is a relative frequency. Now, what happens if we split this into 2 beans? So instead of 1 big bean with 10 kilograms, we'll use 2 smaller beans with 5 each, okay? So let's calculate the frequencies. So f1 will be 3, right? So here we have 85, and we have exactly 3 values which are between 80 and 85. So that's 3. And f2 will be 1. You can see it here. Okay. So the relative frequencies will be 0.3 and 0.1. So we can make a new drawing here. We have 80, 85, and 90. So the first, this is 0.1, 0.2, 0.3, and 0.4. Then this is the first bar, and this is the second bar. So you can see that the height of both bars is getting smaller comparing to the original one. Why? Well, because we have smaller beans. The smaller beans, it means that's less number of values. Less number of values, it means that the relative frequency will be smaller. So every time you use more beans in the relative frequency distribution, the height of all bars will getting smaller, 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 and so on. Now let me show you how density react to these changes. So it means that if we want to use density distribution, we have to calculate the height of bar as densities. And we know that density, let's take the first case. So the density, it's a relative frequency divided to the width of bean. Okay. So in our case, the relative frequency is, for the first case is 0.4. And the width of the bean is 10, so it's 10 kilograms. So that will be our density, 0.04. Okay. So we can make a drawing, similar drawing here. So we have 80, we have 90, then we have 0.01, 0.02, 0.03, 0.04. So this is 0.04, and that will be the bar. Okay, the area of this bar corresponds to the relative frequency 0.4. Okay. Now let's see what happens if we split this. If we split this bean into two, like we did before. So we have 80. We have 85, and then we have 90. Then we have similar 0.1, 0.01, 0.02, 0.03, 0.04, and I will add a couple of more. Okay. So what will be the density for the first bean? Well, we know that the frequency was 3, so the relative frequency is 0.3. So the density d1 will be 0.3 divided to 5. Now you see that the width of the bean is twice smaller. It's not 10 anymore. So it will be 5, which gives us 0.06. Okay. The second density, 0.1, because we have the frequency is 1, the relative frequency is 0.1, divided to the same width of the bean, which gives us 0.02. Okay. Now I will make the drawing. So this is 0.06. This is 0.04. This is 0.02. Okay. So the first bean will be 1.5 times higher than the original one, and the second bean will be twice smaller than the original one. But if you calculate the average height of these two beans, it will be exactly 0.04. So when you use more beans for the density distribution, the average height is always the same, but you can just see some details. For example, in this case you saw this as one big bar, and in this case you see that actually the density in the second sub-bean is smaller than the density in the first sub-bean, but the total density is equal to the density you have in this case. Okay, and that's one of the important properties of the density distribution. So the average height of the bars is always the same. Okay, another property is following. Think. We have relative frequencies, right? So let me make another distribution like this. We know that area of each bar corresponds to the relative frequencies. So we have like relative frequency here for the first bean, relative frequency here for the second bean, and so on. What happens if we take a sum of all areas? So total area of all bars. We know that area of each bar is a relative frequency. If we take the sum of all relative frequencies, we'll get 1, because it's 100 values. So the total area of all bars in the density distribution is always equal to 1. And that's another important property of density distribution. Once again, for visual point of view, it doesn't matter which statistic to use for the making histogram, frequency, relative frequency, or density. The shape will be always the same. It's only the scale that will change, the Y scale. But density distribution is very important for understanding some theoretical distributions that we are going to learn. So that's why it's important that you understand what density distribution is.